Oh, yeah, you were probably thinking to yourself, hey, we're doing arithmetic. Isn't there like something called like geometric? Are we going to get to that? Please educate me. Now's the time. Geometric sequences and series. Let's go for it. So first off, we're going to do a little exploration, right? So get your compasses out because we're about to explore some new mathematical territory. Okay. Let's see here. We're going to try and find a formula for each one of these sequences below. Okay. Some of them may be arithmetic. Some of them might be something different. So for the first one, I go from 1 to 3 to 5 to 7 to 9. I'm going up by 2 each time. That is most definitely arithmetic. Okay? My formula for that, well, I'm going up by 2 each time, so 2n. And how would I start at 1 for my first term? Well, 2 times 1 is 2, minus 1 would give me that 1. Then 2 times 2 is 4, minus 1 is 3. 2 times 3 is 6, minus 1 is 5, so on and so forth. We're good. We got the formula. America. Okay. Next one. 1, then 3, then 9, then 27. That's tripling each time, right? I could define this recursively, so this is not arithmetic. I could define this recursively by saying a sub n is equal to the previous term multiplied by 3, okay? Where a sub 1 is equal to 1. So if I wanted a sub 2, that would be 3 times a sub 1, gives me 3. If I wanted a sub 3, 3 times a sub 2, which was 3, gives me 9, so on and so forth. Okay, we did that one recursively, the previous one explicitly. That's fine. The next one, I've got 1, 2, 3, 4. I'm always going up by 1. Yeah, that's arithmetic. So a sub n is just equal to literally just n. Cool. It's just the term number. The next one, 1, 2, 4, 8, 16. Again, this is it's doubling each time. So now I would have 2. Yeah, 2, then 4. Yep, so it's doubling each time, right? Instead of a sub n minus 1. Sorry, I was making sure it wasn't like doing something different. All right, where a sub 1 is equal to 1. Okay. But perhaps we can write these maybe differently. Let's see here. So 2 and 4, or sorry, B and D, not 2 and 4. B and D. I don't know why I did lowercase and uppercase. Those are geometric sequences, okay? What's happening there? Well, they're multiplying by a common number. Multiplying by a common, we'll call it ratio, or common, we'll say it's a common number for now. And then, so that's what's different, right? How are they different from arithmetic sequences? Well, we're multiplying rather than by adding, right? We're multiplying by the same number rather than adding. And add by a common number. By a common number. Hashtag YOLO. Okay. Lovely. So when the ratio, if we pop down here, so when our ratio of successive terms, right, of a sequence is the same number, same non-zero number, we call that a geometric sequence. Okay? So if I'm multiplying everything by 2, or if I'm multiplying by 3, or multiplying by a third, or multiplying by 4/5, I don't know, right? That would be geometric. I'm always multiplying by the same thing, whether it's a positive number, a negative number, a fraction, whatever, as long as it's not 0. So we can define it recursively by going with a sub 1 is equal to a, our first term, some number a, and that's equal to the common ratio like we had in the previous ones where they were 3 and then 2, multiplied by the previous term. Now that common ratio is calculated by taking a term and then dividing by the previous one, okay? That was a bell in the video, not for reals, unless it's synced up and you happen to be watching this and the bell went off. That's crazy. So if I look at like part D here, if I did 8 divided by 4, that's 2, right? That's my common ratio. 4 divided by 2, that's 2. That's my common ratio here. All right? And that's what we got with geometric. So here we got the number a sub 1 is the first term, and the non-zero number, r, is called the common ratio. Before it was the common difference, common ratio. Boom. I like it. It's awesome and fantastic. Okay. Next, show that the sequence is geometric. List the first term and the common ratio. Okay. So my first term, is 2. Common ratio, I can take any one of those numbers. I'll do 8 divided by the previous. That's 2, which gives me 3. My common ratio, is 4. So that's my common ratio. 32 divided by 8 is 4. 128 divided by 32, that's 4, right? So that's my common ratio. So the recursive formula then would be that a sub n is equal to 4 times a sub n minus 1. So there we go. Sorry, I had somebody barge in there. I lost my train of thought as to where I was. But there's our recursive formula, right, where a sub 1 is equal to 2. We already wrote that down, though. Lovely. We're going to multiply that previous term by 4. Next one. Ooh, go the other way. You already gave us this. Expand. So first term, I just put in 1 for n. 2 to the first power is 2 times 3 is 6. So t sub 1 is 6. My common ratio. What that? Let's wait a sec. If I plug in 2 to the second power is 4 times 3 is 12. And then 2 to the third is 8 times 3 is 24. 2 to the fourth is 16 times 3 is 48. What's happening each time? It's doubling, right? So if I took 12 divided by 6, that's 2. 24 divided by 12, that's 2. 48 divided by 24 is 2. My common ratio is 2. It's not that 3 that was there, it's the 2. Okay, so that is easy to mix up when we're first introducing this, okay? It's that number, the base of the exponent there. That would be our common ratio. Dope. All right. So let's find a formula for a geometric sequence, but like an explicit formula, right? Not the recursive formula. So let's take a look at what we have right here to help us write it out. So a sub 1, we could write out as a sub the first term times the common ratio to the 0 power, because that would just give me 1. Anything times itself is, or anything times 1 is itself. Then to get to the second one, I would do a sub 1 times my common ratio, multiplied by my common ratio. That would give me the second term, right? And then to get a sub 3, I would do that previous term, a sub 1 times r, then multiply it by r again, which would give me a sub r squared, right? And then to get the next one, I would take that a sub 1 times r squared from the previous, right? Multiply by r again, which would be a sub 1 times r to the third. And that pattern would continue on. But what do we notice here about, let me get a different color here. This, that'd be a 1 right here. And then, it's always 1 less. Always 1 less. So perhaps what we could do is we can say, well, I'm going to take my first term, I'm going to multiply by my common ratio and raise it to the term number less 1, right? So 1 less than that term that I want. So if I want the 8th term, I'm going to be raising it to the 7th power. If I want the 100th term, I'm going to be raising it to the 99th power, right? Where r does not equal 0, right? It's a non-zero common ratio. Take the previous term and multiply it by the common difference. Cool. I don't know why I just underlined that. That's old news now. We got our formula. That's awesome. Fantastic. We'll be given YOLO. All right. Make sure you have it. Jot it down. Write it down again. Highlight it. Glitter it. I don't know. Okay, cool. So first example here with the, well, I guess example 2 now, but now that we have this formula, given a sub 1 is equal to 6, and our common ratio is -4, write the rule for the geometric sequence and list our first 5 terms. Do we think we can handle that? I think we can. Okay, so I would have a sub n is equal to my first term, 6 multiplied by my common ratio, -1/4 to the n minus 1. There it is. That's all we wanted here. Okay, cool. Now the first 5 terms, if I plug 1 in, obviously that's going to be 6 because that is my first term. If I plug 2 in, now that's -1/4 to the first power, which is -1/4, times 6 So it's negative 6/4, negative 3 over 2. Whew. That was scary. Fractions. Now if I square it, okay, or sorry, if I raise it to the third power, hold on, let me backtrack. If I plug 3 in for n, right, that'd be 6 times negative 1/4 to the 3 minus 1. Okay, now we have that jotted down. So that's really like raising it to the second, right? So if I'm squaring negative 1/4, that's positive 1/16. So 6 times 1/16 would be 6/16 or 3/8. Deep breath. Now to the 4 for n. So I'm cubing it, which would be negative now. Cubed would be 1 over 64. 6 over 64 reduces to 3 over 32, but it is negative 3 over 32. These fractions are crazy, man. Now to the 5th, or to the 5 for n, which would be to the 4th power. So it's going to be positive now. We do see that alternating positive, negative. Okay, so 4 to the 4th is 120, no, 4 to the 4th is going to be 256. So 6 over 256 will reduce to 3 over 128. That was a beast right there with all those fractions, but we did it, okay? We did it. That was awesome. Next one. Write the rule for the nth term and find the 9th term of the geometric sequence. The 9th, yeah. I don't know why we said that multiple times. Okay. So how do I find my common ratio? Remember, I can take one term and divide it by the previous. I think 2 divided by 3 would be the easiest, right? So I got a sub 1 is equal to 3. R is going to be 2 over 3. Done. Okay, I got that. Easy money. And then I've got a sub n is equal to 3 times my common ratio raised to the n minus 1. So there's, boom, the rule for the nth term, right? Now, if I want to get the 9th term, I'd plug 9 in. So let me change colors. It's getting a little monotonous. A sub 9 is equal to 3 raised to the, 3 multiplied by 2/3 raised to the 9 minus 1. So that would end up being, I've got it jotted down, 256 divided by 2,187. I didn't do that in my head. All right. Awesome. Fantastic. So we could also write a recursive formula for this one, can't we? What are we doing each time? I'm just multiplying my previous term by 2/3, right? So I'd have a sub n is equal to 2/3 times a sub n minus 1, where a sub 1 is equal to 3. That would be my recursive formula. Okay? Dope. You don't necessarily have to have these parentheses here. I kind of like it, but you don't have to have it. To each his own. Now, much like arithmetic, we eventually started diving into, let's find the sum of the first n terms, or whatever it might be. So that's what we're looking to next, is how would we add these up? All right. So first up, we got our sequence that's separated by commas, series separated by addition, subtraction, right? Finite, it ends. Infinite, it goes on forever. Nothing to do with the fractions here, okay? Nothing to do with that. You can have an infinite sequence that would have gone on with the integers 2, 6, 10, 14, so on and so forth, okay? So infinite just keeps going. Finite stops, all right? So if we want to find the sum of the first n terms, that'd be doing s sub, or we'd say a sub 1 plus a sub 2 plus a sub 3 plus, actually, why don't we write it like this? A sub 1 times r, right? And then a sub 1 times r squared for my third term, because it's 3 minus 1. And then plus, we'll generalize this, a sub 1 r to the n minus 1. Okay? That would take care of everything, no matter how many terms. So my sum, if we plug that in, then we could use our calculators for this. A sub 1 times r to the k minus 1 within my summation. Okay? There is a wonderful, fantastic formula. All right. So we've got our first term multiplied by, we have a fraction here. It would be, I'll put this in parentheses as well, 1 minus r raised to the n over 1 minus r. R being my common ratio. We don't want it to be 0 or 1 in this case. And this is for a finite series. Okay. If it was 1, it wouldn't be changing, right? It would be the same number every time. If I multiply by 1, it doesn't change. So what's the point? It's not being 0 or 1, and that is finite, right? It ends. It ends. There's a different formula for infinite, but we'll talk about that later when we start talking about converging and diverging series. Okay, cool. Let's keep moving. Find the formula for the sum. Make sure you jot that down there. Jot that formula down. Find the formula for the sum of the first n terms of the sequence 3 to the n. Then use that formula to find the sum of the first 8 terms. I am just going to go right to, I don't really care for this too much. I'm going to go, let's find it for the first 8 terms. Let's do it. Let's deal with finite first. It's a little more, I feel like it's more doable that way. So let's see here. So it's 3 to the n though. We do want that. So my first term would be 1, or sorry, 3. 3 to the first is 3. 3 to the second is 9. 3 to the third is 27. And we want that just going on and on and on, right? Or only first 8 terms. So my sum would be 3 times, and then be 1 minus, my r is 3 raised to the n over 1 minus 3. And so this would be the n terms. So if we did for the 8th, so I guess we kind of did the n terms. It wasn't too crazy and weird. I would just replace that n with an 8. And then I plug all this in to my fancy-dancy calculator. All right. So I end up getting, I have this worked out, 9,840 when we plug that all in. Make sure you're probably doing things. You might want to throw an extra set of parentheses in your calculator. You can do that, get that fraction done, multiply it by 3. Whoop, whoop. Awesome. Fantastic. Wonderful. All right. Find the sum of the finite series. So in my formula, and I like to jot this down off to the side first so I can fill things in. I'll put this over here. So we don't know what, we know, hold on. Our common ratio, I could figure that out. 125, how am I doing this all the way over here? 125 divided by 625. I think that's 1/5. Right? So 1/5 would be my common ratio. So I've got that. My first term is 625. So 1 minus 1/5 raised to the n. I don't know what the n is yet. 1 minus 1/5. Okay. So I don't know the n. I need to figure that out, right? I need to know how many terms we're adding together here for this formula to work. So I need to solve for n. Is there a way I could do that? Let's think. Well, 1 over 125 is my last term, right? So if I set this equation equal to, where I'd have 625 multiplied by my common ratio of 1/5 raised to the n minus 1, I could solve for n this way, right? I'm trying to figure out what term number is the 1 over 125. Awesome. Well, let's do it. So let's see here. I would need to divide by 625. Oof. We're going to be dealing with some crazy big numbers. Okay, so I end up with that. Got my calculator handy here. And now I would have to solve for my exponent using logs. Don't you love pre-calc honors? Okay, so I'm going to have log base 1/5 of 1 over 78,125 equals n minus 1. If you forgot how to do this in your calculator, math, alpha, math, if you've got that. And then we'd have the 1/5, and then we'd have 1 over 78,125. I get 7 equals n minus 1, so n equals 8. Hey, that wasn't too bad, right? Got my n. Now I can substitute that in. boom, 8, boom, 8. Now I can plug that whole right-hand side into my calculator, which I have worked out. We've got, let's see here, and we end up getting 781.248. There's my sum. Cool. So kind of similar with like the arithmetic, just we're dealing with a different formula. We end up having to find our common ratio, like we did our common difference. We have to find the number of terms, like we did as well. So very, very similar. Okay. Now, let's get to these bad boys. So we got a couple options here. One, if you got the summation tool in here, awesome, more power to you. If it asks you to write it out, this is third hour, so there's all these lunch periods and all these bells. Sorry, I apologize. We can write it out. So here we want the first 6 terms, so I'll show it written out. We'd have 32, that's my first term, right? And then 1 minus my common ratio of 1/4 raised to the 6th over 1 minus 1/4. Cool. And that's it. So if I plug that in, I get 1365 over 32, or approximately 42.656. Either one of those, Gucci. Or you can plug it into your calculator as it is. The big thing to not mess up in your calculator is not going outside of the given parentheses, okay? So if you are using your summation, let me make myself giant here. If you are using the summation there, do not go outside of that set of parentheses to add like exponents or anything like that, okay? Be very careful about typing those in. If you want to try that now and make sure that you do get the same answers. If you go outside of those parentheses, bad things happen, okay? It takes whatever it is inside there and then it multiplies it by whatever you put out there. So do not go outside that given set of parentheses for anything. Cool. Next one. All right. So why don't we try, I'll actually plug this one in and show you. And again, I'm sorry, but my emulator does not have this functionality here. So if I am sitting inside here in that given set of parentheses. So I'm going to type in 500. Okay. Now I'm not going to arrow out of that set of parentheses, right? See how it gives me the option? I'm not going to go and throw the 1.04 raised to the n minus 1 out here. I need to be inside the parentheses here. Okay. So I'm going to open up another set of parentheses, multiply by, and then open up another set of parentheses and do 1.04 raised to the x minus 1. And then, as you can see here, I still have the original set of parentheses out around the 500 and the very end there, okay? That's huge, okay? Cannot go outside of that. All right, if we hit enter, I should get the correct answer. Yeah, 4,607 point something. One sec, let me jot it down. And there we have 4,607.11313, so on and so forth. All right. Cool. Awesome. You can use the formula. You can use your calculator. If it asks you to write it out, then you need to write it out. So you do need to be, savvy with both. But there we go. All right. Last one. If someone went back through 10 generations, how many ancestors would she have? 2 parents are 1 generation back. 4 grandparents are 2 generations back, etc., etc. So we'll keep it like super consistent like that. Obviously, that's not always the case. Not everything is the exact same, but let's say that is the pattern that has been followed in this particular family for 10 generations, right? So you've got you, and then you've got parents, right? And then you've got grandparents. Your parents' parents, right? And then further than that, right? Great-grandparents, their parents. And again, we're saying that this is the pattern for this particular family for 10 generations. It was consistent. I don't think that's really the case, but whatever. So we've got, let's see here. So for how many ancestors she would have, we're going to start here. So that'll be our G1, right? Generation 1, and we'll say there's 2, right? And then we have generation 2, that's going to be 4, and then 3, that's going to be, it looks like 8, so on and so forth, right? So 2, 4, 8, 16 is doubling each time. So if I want 10 generations, my first is 2, then be 1 minus, my common ratio here is I'm doubling each time. So 2 raised to the 10th over 1 minus 2. And if I were to plug that in, we'd end up with 2,046 ancestors. My goodness. That's crazy. It's a lot. It's a lot of people. It's a lot of people. Double, double, double. Imagine if that was like money. Say like you doubled your savings every single day. By the 10th, you know, it would add up to 2,046. So you can think about that as money too, right? If I put $2 in my savings account, then I'll make it to 4, then 8, so on, so forth. Add them all up. It's a lot of money. All righty. Thank you for tuning into this TED Talk. I hope you guys have a wonderful day. We'll finish up some more geometric stuff in the next one. But for now, America, freedom, rock and roll, Costco, Yo-Ro, and Riverdog J on the gram. Deuces.